Okay. Hello, everyone. Welcome back. I hope that everyone is back. And so now we are going to look at the format string vulnerability exploit, which is same as what we discussed on the slides. I hope that if you had any doubts at that time, then they will become clear with the help of this demo. And you can implement the same this you can modify the same demo afterwards, and you can try to override some location of your choosing afterwards, and by using this percentage n format specifier. Okay, and currently we will today, now in this demo, we are only going to look at how to read the value of this secret string, which is a global string, which is basically storing a secret message. And so let's get started. So uh, this is the same for program that we had looked earlier. We have this str, which is a global function, so a global array, and it is storing the secret message. Then you are here going to create a user string inside your main, which is a local array in the main local character array. And what you're first, you're just setting everything in this array equal to 0, and after doing that you are going to copy a format string into this array. Now here, as I've already mentioned, and I would like to again repeat that in for this particular example demo here, we are filling this user string directly with the with str copy and writing this format string here. But in a real world exploit, this will not be kept. This will not be a part of your program, but instead it will be provided by the attacker via the interface, via, for example, the user input, or via the network. When your program is expecting any input any external input, then the attacker can, and if that input string is being fed to the printf function, then that can be exploited. Okay, so then is this input string, if we look at it again, then the first 4 bytes is an address. And here in this example, this is actually the address of this string. And we can find the address of this string using GDB. When the program is running, we can actually print the address of print the address of the variable. And then we will have to actually see where this user string is placed, like where this user string buffer is placed. And then we will have to see uh, with respect to the printf stack frame, we will have to, and the argument which are being passed, we will have to see that far is your how far is your user string buffer from the argument pointer which is being passed to printf. Okay, so let's inspect that, and then we are going to now run this with GDB, and then we are going to see all of the, like, we are going to inspect the stack. Okay, so let's run the pre-compiled binary that we have here. This is now running. First, let's just run this and see what happens. So yeah, so when we run this binary, then first we are going to print some random content from the stack, and then afterwards it prints the secret message which is stored in the global variable s, or the global variable string. Now let's list this program, and this program is here, and let us just add a breakpoint here so that we can check what is the address of this str string. So we can just add a breakpoint on line number 7 here. Okay, and then let's disassemble this, and sorry. Yeah, I'm sorry, I've not started the program. So let's start the program with R. And when we start the program, then now it's running. So then we can disassemble and then we can see here. And if we are going to look at the code, so yeah, so your string, yeah, your string, yeah, so your string user string is actually here like this is your user string. The user string here is of 100 bytes. Okay, so your user string is of 100 bytes, and yours on the stack, it's allocating 70 hexadecimal, that is 16 times 7 bytes for this user string. After that, we have this call to memset to set it, and then there is this call to printf. So that's how your code is. Now let's print the value of, I think it should be, let's see. Yeah, so when we print the value of str, it is prints this secret message is there, and let's try to print the address of str. So if we print the address of str, it is 804A04 0. Yeah, and that's what we have put here. It's yeah, so it is actually uh 804A040 means in the beginning we'll have to append a 0. So then it will become 0804A040. And that's what we have stored here, 0804A040. So this is the address of the string which we are going to write in this user string first. And then we are passing this user string is placed on your stack, right? And then after that, it's going to call. So let's now let's execute some instructions. So for that, let's add a breakpoint here. And note that here you are passing push EAX. So you're doing push EAX. So EAX will have actually the address of a user string here, because you're passing user string as an argument to printf. So this is actually pushing the argument. So this is pushing the argument, which is the pointer to the format string, and your format string is in the user. Uh, your format string is in the user string buffer. So let's execute till here. P. Uh, so we have added a breakpoint till here. So let's just continue it and let's see now. Disassemble and let's make sure that we have reached here. We're just before the printf. We have not yet pushed EAX onto the stack, but let's see. Now let's try to print the value of, so the local variable here is your, so let's see the local variable. So user string is your local variable. And let's try to print the address of this string. So the address of this string is FFFD2FC. Okay. So this is the basically this is the address to your format string, and this is being passed in EAX. So let's see if these are equal or not. So yeah, so these two are equal. So EAX contain this value only. So that means to the print function, you are passing the address of the user string. Okay, and your user string contains is like contains these values. Now we are going to let's look at the stack. So x32x roller ESP. So this is how your stack here looks like. And uh, so that's how your stack look like. And you have created a you have mem set, and then you have moved these values also, right, into the stack. So yeah, so here. Yeah. So here is the address 8048040, which is the address of the string, right? This is the address of the string. And after that, you will have these uh, percentage X, and I think, I think 20 is space. 78, 7, 25, 20. So I think 20 is space, then 78 is percent, then 25 is X, then space, and something else. So yeah, I mean, it's stored in the Little Indian format. So, but it is like percentage X, it's storing percentage X and so on. And then I think here it's storing percentage S. So it's S. So now it's storing here percentage X is followed by percentage S, and this is actually your uh, address, which you have placed in the beginning of your user string. So this is stored on the stack, starting from here. Now, when you are passing the pointer, so this is your pointer to the user string, right? This you are passing to printf. So this is the argument you are passing. So then you will, let's do one more instruction. Let's execute one more instruction. Then this instruction executed. Then let's see. Yeah. So this is the pointer to this user string. Okay. Pointer to this user string, which is D2FC. So this is D2F0. This is D2F4, this is D2F8, and this is D2FC. So your user string is starting from here, and this is your pointer to this user string. So your argument pointer, this is going to be, this is your format string. So your pointer inside the format string will be here, and your argument pointer will be here. Okay, your argument pointer will be here. So when you will execute now printf, it will start printing. First, it will print this value. Then it will start printing percentage x's from here. So now, as you can see, that why do we need 6 percentage x's? Because there are 6 values in between. There are 6 4-byte locations in between here. So first percentage x will print this value 0, then 64, then this value 8048469, then 0, then 1, and then this value. So let's look at the output that we had got, that we had gotten before. So this was your output. I'm just copying it for comparison here. So first it is going to print this value 8048040. And I think this is printing it like the symbol. Okay. After that, it is going to look at next format specifier, which is percentage X, and it will start printing from here. So it will print value 0, then 64, then this value 8048469, then 0, then 1, and then this value F7, this. Next, in your output, I should have copied the entire output. It was this secret message. Here, this is your, it's printing secret message. Now, why it's printing this secret message? Because when you have printed this percentage, when have you have printed this value? So you have printed percentage x's to 6 times, and then you reach at this location. And then next format specifier is percentage s. So printf is going to take this value here and treat it as an address, and then it is going to start printing from this address. And this is the address of your global string. So it will start printing and it will print this secret message here. So that's how it is working, and that's how we will have to look at uh, the stack, and we'll have to see how many bytes away is your uh, argument pointer here is from your pointer inside the format string. And you will have to craft your format string in that way. Is there any doubt? So is there any doubt in this demo? Let's continue. So it will finish executing and we are able to print the message. We are able to print the value of some location without any error. Okay, so now this was format string vulnerability, and I encourage you to go and try this demo. So you can uh, download it from GitHub and you can try it, and then you can try to modify it and see if you can store some value in some location on the stack or anywhere else. You can try to find the address of some local variable, and then you can use the same approach with percentage n, and then you can try to change it. So that's if there are no doubts, then I will then end this demo, and then we can look at the next topic, which is the defense control flow integrity. And so let me know if there is any doubt in this. Can we modify instructions using this technique? No, you cannot modify instructions in this using this technique if you assume that W XOR X is present. Otherwise, I mean, if W XOR X is present, then your code segment is non-writable. If the code segment is say not non-writable, if you can write it, then you can modify. Does that answer the question? Does anyone have any other questions? Okay, so then um, so let's do this before I move on to CFI. Let's try to fill this table because we have done these and we have looked at these attacks. So we can try to fill this. So with the format string vulnerability, can we read at local variables from other function foo from another function like foo bar? So yes, local variables from the other function foo. Yeah, local variables are also located like on the stack only. In this particular demo, which we saw was for the global variable, which is like stored in the heap. Uh, and so the local variables are there on the stack. You just would need to know the location of those local variables. But like currently, you would just need to inspect the stack and know exactly where the local variable is stored. Yeah. So you can read anything as long as you just need the address of that place. Okay, so let's try to fill this table, which is here. Yeah, so I hope that it's visible and it is big enough. And that the question that we have to answer here is this: can the defense prevent the attack? So since we have discussed this different kind of attacks and these three actually defense techniques so far, and I plan to look at these two next. So first of all, let's fill this. So the W XOR X. First of all, the W XOR X defense is actually enabled by the OS. ASLR is also implemented by the OS. Stack canary is a compiler-based defense. And the next two that we are going to look at are also compiler-based defenses. So compiler-based defense means that the compiler is going to add new instructions into your program to enforce that defense. While in case of W XOR X and ASLR, you're not going to add any new instructions into your program. The OS is going to enforce that the pages which are executable are not writable and the data pages are not executable. And at the load time also, so the OS is going to ensure that the pages, the segments, etc., are randomized. So now let's uh, look at these. So the first type of memory exploit is data corruption, like local variables. If you're there, if you exploit the buffer overflow vulnerability to write beyond the bounds of your buffer, and if you change the local variables, then the question is, can W XOR X prevent that? So let's do this as a quiz, and I hope everybody can answer. Yeah. So the if the W XOR X is even when W XOR X is enabled, the data corruption attack cannot be prevented because with buffer overflow attack, we are just changing the data values. We are not writing any new code. So it does not prevent. So W XOR does not prevent the data corruption. Now, does it prevent the execute code on the stack, which we have implemented with buffer overflow? So does it prevent W XOR does W XOR X prevent execute code on stack exploit? Yes. So it prevents it because the stack is no longer executable. Then the return to libc. Does it prevent return to libc? So what were we doing in return to libc? Uh, yes. So the answer is no only. It does not prevent the return to libc attack. And it is so because in return to libc, we are not executing anything from the stack. We are actually only changing the return addresses to invoke functions in the libc. Okay, we are going to change the return address to a function address in the libc. So it does not prevent return to libc. What about return oriented programming? Yes, so that is also right. It does not prevent return oriented programming attacks also. Then what about format string or exploits which corrupt the local data? So again, I think we will all agree it does not prevent. It's same as before, right? Yeah, so it does not prevent it. After that, what about format strings which corrupt the control data, such as the return addresses, function pointers? Yeah, so it does not prevent that also. So now coming to ASLR, what about ASLR? ASLR is basically randomizing everything. So I think what we can say, what can you say about ASLR? Can you make a general statement about ASLR, that whether it prevents uh, the attacks or not? Yeah, so yeah, you're right. First, data corruption can still happen, and also it's right that it makes it more difficult to exploit the. So that's everything is right in terms of ASLR. Actually, it's we cannot guarantee whether the defense is prevented or whether it is not prevented. It all depends on the randomization. So if it also depends on, say, uh, which modules or which components are randomized, whether it is randomizing all of the like segments like stack, program, or the heap, etc. And even on the stack, whether it is randomizing, like adding a random padding between different stack frames and different stack variables or not. So that all depends on how it is implemented. So for ASLR, what we can say is that it has, it may or may not prevent these exploits. Okay, it is, but it makes it harder for the attackers to do these exploits. So for ASLR, we will just say that it may prevent the exploits, all of them. So the local data variables, if it for that, it would have to know exactly where which local data is stored where, right? If there is padding, then it may not be able to change it appropriately. Uh, or for the control data, like return addresses, also it would need the address of that uh, return address where it is stored. And for return to libc and ROP kind of attack, it needs to know the address of these library functions. And if these library functions are every time, uh, if the if these, like, say, text segments and etc., if they are randomized every time, then that will change the location of the library functions or every time, or the gadgets every time, and therefore it is harder for the attackers to do any exploits. Now coming to stack canaries now. The stack canary, we saw that It's a compiler-based defense where the compiler has added additional instructions into your program. And in the beginning of any function, the compiler is going to add a canary onto the stack frame of your function. Like say if foo is called, then when you start executing the foo function, then when you go inside the foo function and first create the stack frame for foo, then the first then soon afterwards, like this, your compiler is going to put a stack canary there. And then when the function foo is returning, at that time it is going to check for the integrity of this stack canary. Now the question is, can you prevent data corruption with stack canaries? So let's assume when we are answering these questions is that the stack canary value is not leaked. Okay. So let's assume that and then try to answer this question, because stack canary, although it's randomized random data which you are adding, but still the attacker would need to know, say, the location of the stack canary, the value of the stack canary, and would then need to create the exploit in that way. So the data corruption, yeah, so again, this can be both yes and no, actually. So that depends on what the canary is preventing. Okay. So if you put the canary there soon after the return address, then it is going to prevent only the uh, return address. If you put your local variables such as integers and your say function pointer, and then you put a stack canary between the say any arrays and buffers, so that you can, then you will be able to even prevent your local data, which is like integers or say function pointers. But that depends on the placement of the stack canary. So it will then depends. Okay. It can be yes, it can be no, but it's possible. So it is possible. Then execute code on the stack. Can it prevent to execute code on the stack? For this, actually, we just need to prevent the integrity of the return address. And so the stack canary is always going to be placed in the stack frame, and it's always at least going to prevent the return address. So that's why it will prevent. Now coming to return to libc and ROP kind of attack, what do you think about those? Will it prevent those? What do you think about return to libc and ROP class of attacks? Will your stack canary prevent those? You're not executing from the stack. Okay, so one answer is no. Hmm. And why is it no? Why can't it not prevent the attack? Yeah, so it will be able to prevent. It prevents both of these attacks because it's just ensuring, to prevent this attack, we just need to ensure the integrity of the return address. And that's what it is going to do. It's going to prevent the it's going to check it's going to prevent the corruption of the return address. Now coming to the format string, corrupting some local data or some, like say what I'm saying by local, what I meant by local was actually not like in the scope, but what I meant by it that non-control data, I should say. Okay, so format string, if we modify some non-control data, and if we are and then if you're modifying any control data. So as we had discussed earlier in the morning, that non-control data is any data which is not being used for in your control to change the control flow of your program. Control data is any data which can change the control flow of the program. So such as your function pointers, return addresses, and your conditional variables, etc. So now question is that with the format string vulnerability, we saw that we can change the data values at any arbitrary location. Okay, and so that means we can change any non-control data on the stack or somewhere else, or we can change any control data as well. So the question is, will the stack canary be able to prevent that? Mm, yeah, so it cannot prevent it. Okay, and the reason for this is not because it can expose the stack canary. The reason is actually that with format string vulnerability, you can write at an arbitrary location. You don't need to overflow. You're not writing beyond the bound of the buffer. So you're never going to corrupt the stack canary. You just need to know where your return address is located. You're going to create that format string as we saw in the examples, and you're going to specify the address of this location, and then you can fill this location with value that you want. Uh, so that's why it's cannot prevent it, and so that is no. So stack canaries cannot prevent it. And I think that as now, if you look at this table, you'll see that there is still some classes of attack which are able to do, say, the control, which can corrupt the control flow of the program. So like stack canary, of course, I think they are very still a good compiler based solution, as they're able to prevent so many attacks. But still, there are some other classes of attacks which are not prevented with any of the defenses that we had looked at yesterday. And this class of attack can still corrupt the control data or other data of your program and can change the control flow of the program. And in particular, here we are more concerned about the control flow of the program and not about the, say, non-control data here. Control flow, we are more interested here because control flow gives the attacker the capability to run anything actually. Then if the attacker can change the control flow of the program, then the attacker can run any instructions of its choice or like any function of its choice, and then can do more harm. So that's why we are focusing on control flow corruption, and that is the like that sort of motivates that we need another defense. Okay, so we need another defense which is particularly for control flow integrity, to ensure that the integrity of the control flow data which is stored in your program. So that is control flow integrity, which we will be looking at now. And if you have any question to what we have filled here so far, then please let me know. Otherwise, we will look at not prevent control data and then. Okay. Uh, but this statement is not actually clear to me. If you can clarify, you said that for stack canaries, it cannot prevent the control data corruption, and then ROP. So are you saying that stack canaries cannot prevent ROP attacks? Yeah, ROP through string formatting. Yeah, yeah, that is true. Yeah, that is true. That is absolutely right. So we can use this to then change the return addresses on the stack, and can do a ROP attack as well. Yeah, so now I hope that uh, so it was interesting for you all for so far. And now we will look at control flow integrity. Is there any question before I start? Okay, so if there is no question, then we will start looking at CFI. Yeah, so let's look at CFI, control flow integrity. So the first work in which proposed control flow integrity was actually uh, like a paper in 2005. And the area so there has been a ton of work in this area since then. And so this what we are going to discuss today. It's actually the idea from the first paper, which was 2005. And of course there has been a lot of advancement in this area. And control flow integrity, like there has come a lot of variants of this control flow integrity. So we have looked at this control hijacking attacks like buffer overflow, format string vulnerabilities, return to libc, return oriented programming, and etc. And so we this these different attacks, what they are doing is that they are corrupting the control data which is present on your stack, and then they control data such as your return addresses, function pointers, etc. And then they are changing the control flow of your program. Now, CFI is this defense, which stands for control flow integrity, and the goal of CFI is this, what I'm going to read now, is to it's a provably correct mechanism that prevents a powerful attacker from succeeding by protecting against all control flow integrity attacks. Okay, so this is a very like strong, this is a very strong technique, and it is giving us even very strong here guarantee. It's saying that it will be able to prevent all control flow integrity attacks. Okay, and it's assuming a powerful attacker, and we will come to know, we'll look at next that what is this about this attacker model. And this is a mechanism that we are going to look at now. Okay, so this is what we are going to look at now is only a mechanism. Okay, so when we had started discussion yesterday, we said that there are two things in security, like one is a mechanism and one is a policy. So the mechanism is just like you are going to so the mechanism here, which CFI is providing you, is foolproof. Okay, and policy means what you actually implement, what you are going to, how you are going to implement it. So let's say Like in terms of access control, the mechanism can be, say, you are going to give, you're going to, for every resource, you're going to say keep a metrics for every resource where you're going to keep the information of the user, and you're going to then store whether the user has the permission to read, write, access this resource or not, etc. So that is the mechanism that you have. And then you can have some other policies in your system which will be using that mechanism. For example, the mechanism is there, but the policy would be such that maybe you give by default all users on your system the read access on all the files. The mechanism allows you to restrict the access to the files as to say only the user, only the owner of the file, but how you have implemented it actually in your system, those are the policies. Okay, so mechanism means what is possible. The mechanism is what we are going to discuss today related to CFI, but how is it actually implemented? That are policies, CFI policies, and they may or may not be fully, they may or may not give you this guarantee that all attacks are, any attack is not possible. So it will protect against all control flow integrity attacks. That actually will depend on what policies have been implemented. So in CFI, what's the idea is that during the program execution, so when your program is executing, whenever a machine code instruction transfers control, it targets a valid destination as determined by the control flow graph created ahead of the time. So there are many things here. One is this control flow graph, which we are going to look at soon, that what is a control flow graph of a program. And what it is saying is that when your program is executing, okay, and whenever the machine code instruction is going to transfer control, like if there is a branch instruction, if there is a call instruction, if there is a return instruction, then whenever this machine code instruction is going to transfer the control to a location, then it targets a valid destination. Now, what is a valid destination? That also we are going to specify that what is a valid destination. So in CFI, the CFI control flow integrity is saying that during your program execution, whenever your program is executing, and when there are these machine instructions which transfer the control, such as your return instruction, branch instructions, call instructions. So whenever these machine code instructions transfer the control, then the destination of the these branch instruction is always a valid destination. So it targets a valid destination. Now, this valid destination is determined by a control flow graph. It's determined by a control flow graph created ahead of time. Okay, and it will become more clear as we look at it in the next few slides that what is a valid destination, what is a control flow graph of a program. And before we move forward, let us define the attacker model here. So the attack model or the threat model is here, assumes that attacker is very powerful. So the attacker is powerful in the sense that the attacker can at any time arbitrarily overwrite any data memory or registers. So like in format string vulnerabilities or exploit, we as an attack I as an attacker can exploit it, and I can write any arbitrary data memory or any arbitrary registers, right? So we are saying that the attacker is powerful, and the power the attacker has to write any arbitrary data memory. However, the attacker cannot directly modify the program counter register, So like it can override most of the registers, but like which are being used, say, but except say this program counter and some reserved registers. And after this, the assumption is also this, that the data memory is non-executable and the code memory is non-writable. So the W XOR X we assume is present. But because if W XOR X is not present, then we will be able to subvert CFI. Now, why is it so? I'll explain again later when we look at it in more detail. But just remember that for CFI to work, it's important that W XOR X is enabled. If W XOR X is not enabled, then CFI defense is not no longer going to work. Okay. So we are building on top of W XOR X. So this defense is built on top of W XOR X, and it gives the attacker the power to write at any arbitrary data memory. So we have discussed the goal of CFI. The goal of CFI is to ensure that during the program execution, whenever a branch instruction is executed, then the target of that branch instruction is a valid destination. I've not yet discussed what is a valid destination, but here it is saying that the valid destination is determined by a control flow graph, which is created ahead of time. Now, what is this control flow graph that we are talking about? And we are going to look at it now. So I am not very sure if you have taken a course in compilers. Uh, so here, uh, so so a control flow graph. So if Yeah, so a control flow graph is just a graph representation of your program, okay? And like any other graph, what are the two things in your graph? There are two things in your graph. One is the set of vertices and one is the set of edges. And the set of vertices here in this control flow graph is the basic blocks, okay? So even if you have not studied about this before, let's define what a basic block is. So a basic block is a consecutive sequence of instructions or code such that the instruction in each position always executes before all those in the later positions. Okay. So, and the second condition is that no outside instruction can execute between two instructions in the sequence. So this is the definition of a basic block. Okay, and the simply what we can say here is what's written here in the black box, that the control inside a basic block is straight. The control is straight. You execute the instructions inside a basic block in sequence, starting from the first instruction until the end instruction, and the control flow is straight. So if you execute instruction 1, then you will go to instruction 2, then 3, and so on. So there are no jump targets except at the beginning. So you can, so you so the only the beginning of the basic block can be the jump target. Okay, so that means only the so from anywhere in your program, the basic if anywhere in your program, basically the any instruction basically in your program cannot call the instructions within a basic block except at the beginning. Okay, only the beginning, the first instruction can be the target of any jump, like can be the target of any branch. Okay, and then there are no branch in your basic block except the at the end of the basic block. So in simply what we can think of it is like a box, like this is a box. So this is a basic block. So this is the example here. So this is, let's say, your code. Okay, this is, say, your code, which consists of these 5 instructions, 1, 2, 3, 4. And when we are going to convert it into basic, like when we are going to form the basic blocks out of this code, then we will have these three basic blocks. And the basic block here, what happens is then when you enter a basic block, then you can only exit from the last instruction. When you start executing from first instruction here, then x is equal to y plus z you will execute. You cannot skip execution of second instruction. You have to go in sequence and execute instruction 2. And you can only exit from the last instruction from the basic block. Okay. Then similarly, this is the second basic block where third instruction is executed, then the fourth instruction will execute, then fifth instruction will execute, and the fifth instruction here is a jump to 1. So it's a jump 1, so that's why we are so since this is a branch instruction, so that's why the basic block is getting terminated here. Now in this case, the first case, there is no jump in the end of the basic block. Then why did we terminate the basic block? Like, why is it a basic block, and why did we not form the basic block like 1, 2, 3, 4, and 5? So that's because the instruction at this line number 6, which was not shown here, is actually a jump to 3. So since it's a jump to 3, so it will jump here. And as we said, that there cannot be any jump targets within a basic block except at the beginning. So that's why we had to split it here and form two basic blocks. Okay, so to reiterate, a basic block is a consecutive sequence of instructions such that there's only a single entry point and single exit point. And once you enter a basic block, you will execute all the instruction inside the basic block, and you can only exit from the basic block at the last instruction. And that's all about the basic blocks. And now when we are going to create this control flow graph, then these basic blocks are actually the nodes in this control flow graph. Okay, these will be the nodes. So again, coming back here, a static control flow graph is a graph where each vertex is a basic block and there is an edge Vi to Vj if there may be a transfer of control from block Vi to block Vj. Okay, so like in this example, here there is a transfer from line number 5 to this line number 1. So then there will be a edge from 5 to 1. And similarly, here there is a jump from 6 to 3. So there will be a edge from 6 to 3. And that will form the control flow graph. These are the three nodes. And then there are two edges here. One is from 5 to 1, and then another is from 6 to 3. That will form the control flow graph. So the control flow graph, when we talk about it, then we can talk about it at two granularity. One is at the granularity of a procedure or a function. Okay, so when we talk about it at the granularity of the function, at that time, the nodes are these basic blocks and the edges are we add an edge if there can be a transfer of control from basic block 1 to the basic block 2. But when we have this big program, then we actually also need something else, and that is called a call graph. So creating a control flow graph for each procedure separately is not enough for us. Okay, so that's why we also need something called a call graph. Okay, now what is a call graph? So in a call graph, the nodes are the functions and there is an edge between two nodes if function Vi calls function Vj. Okay, so here, like if function Vi, even if it conditionally calls function Vj, like it may call or it may not call, still we will put an edge from function Vi to function Vj. Now to make it a bit more concrete, let's look at this example where we have these three functions, orange, red, and green. Okay, the orange function here is calling the red function twice, and then it's calling the green function. And the red function is not calling anybody, and the green function is calling itself green, and then the orange function. So the orange function is going to call red twice, but we here are, let's say, calling like a undirected graph. So we're not going to put anything on the edges. We're just, even if there is one call, and even if so basically, no matter how many calls are there, and even if there is one call, and if that call is even conditional, like it's put inside a if condition, as long as if there is a possibility that function vi can call function vj, we will put an edge. So orange function is calling red function, so we will put an edge here. Then orange function is calling green, so we'll put an edge here. Then the green function is calling itself, so we're going to put an edge here, and then the orange, sorry, green calls the orange. So we have this edge here. So this is then the call graph of the function. Now, is it clear so far? Do you have any question so far with respect to the background, like control flow graph? So first we discussed how we are going to create control flow graph at the function level. Okay, so we are going to take the function, we are going to split the function into basic blocks, where we said that a basic block is a code sequence with a single entry point and a single exit point. And if you enter the basic block, then you have to execute all the instruction in the basic block in the sequentially until you get out of the basic block at the last instruction. And then to construct the CFG for a function, we have to, what we are going to do is that we are going to add an edge between these basic blocks if there may be a transfer from block Vi to Vj. So see, so please emphasize on this word may. So it's like if it's possible, like if even if it's like a condition, conditionally, if it's possible, like it may go, it may not, like a if condition. So the condition may be, if the condition is true, then you may go to block number 2. Otherwise, you may go to block number 3. So even if it is conditional, you're going to put an H. And then we said, okay, that is okay for a single function, but we're not talking about a single function. We're talking about the whole program, which contains these functions, right? Many functions. So then we need to have a call graph. Now, why a call graph? Because when, how can we then basically stitch together these functions? How are the functions related with each other? So the functions are related with each other when one function calls the other function, right? So that's why a call graph. So we are going to inspect each function, and then we are going to check that which functions are being called from this function. Like for example, here orange is calling red and green. So we are going to put an edge from orange to red, and then an edge from orange to green, and see that it is a directed graph here. Okay, so it's a directed graph that we are creating, and it's a call graph. And also here also it was a directed graph. So then we have so now we have these two things, two different things. One is the control flow graph at the function level, and one is the call graph at the program level. Okay, there are two different graphs that we have so far. One is a procedure level graph, one is a call graph. Is there any doubt? Okay, so then we are going to create a super graph, and which will be like basically our CFG for the program. And we are going to create it by superimposing the CFG of all the procedures over the call graph. So how are we going to create it? Is basically like, let's say if this uh, orange if this orange block here is say representing So is the orange function, right? The orange function, which has these three call instructions. One first is the call to red, second is the call to red, third is the call to green. Then what we are going to do is that we are going to add an edge from orange to red. Okay, and here we are actually going to add an edge from orange to red, like the first instruction, like the first basic block, the entry basic block into the red function. Okay, so here now this red block which you're seeing here, consider it like the graph which we created for the red function. So we have created this graph for the red function, right? Like the per procedure level, we have created this graph when the nodes are the basic block, edges are between the basic block. Now this box here is representing that graph. And so basically these are again this is also that graph that we have created. And then we are going to look at this call instruction, and then at the location of this call instruction we are adding an edge to the entry basic block, and then from the exit basic block we are going to add a edge back here. Similarly, the second call is also to uh, the second call the second call here is also to the function red. So we are going to edge to the entry basic block in red, and then we are going to add an edge from the exit basic block back here. So this creates a context sensitive graph, super graph here, uh, where now what is the meaning by context sensitive? I'll come to that in next few slides. But this creates a super graph, okay, where the where now what are the nodes? Can you tell me what are the nodes here in this super graph? What is this node? Yeah, but one level above actually. So the node, it's like the super graph, okay? And so here now actually I'm saying that this particular block is not is the entire CFG of that procedure red. So it's the entire CFG of that procedure red, where the basic blocks were the nodes and the edges were between the basic block. That entire CFG I've put here in this red block. Okay. And similarly, this also orange also, this is the entire CFG of orange. But we have stitched them together, like we have like we with the help of this call graph, we have stitched them together by looking at every call location, and from every call location we are going to uh, put an edge to this CFG of the red function and then back. So this is so, and in the last slide we actually said that this is a context sensitive function. Okay, so why, sorry, this is a context sensitive super graph here for orange. Uh, why is it context sensitive? Is because it distinguishes between the two calls to the red. Okay, so there are two different calls to red functions. And why is it important to distinguish between the different two calls to red function is also will become clear in a while, but it's context sensitive in the sense that the red function, when it's called from line 1, that is being treated in a different, like that, for that we have different edges. We have different forward and backward edge. And then when it is called film line number 2, then again we have different forward and backward edge. So the different calling contexts are distinguished. So that is why it's context sensitive. That graph was context sensitive. Now let's try to understand it better with an example. Okay, so let's say that you're calling this function id from these two different locations. First is calling it with value 4, second one is calling it with value 5. Okay, and let's say that this is a context sensitive uh, this is we are doing it in a context sensitive manner. So what does that mean is that when we are calling it from id number 4, then we are calling this function id, and then when we are returning back, then the return edge which we have in the graph, we have actually labeled it. This is a labeled edge, and we have labeled it with value 4, indicating that this uh, function call was from this location id 4. And then similarly, when we call it from this ID 5, then this will go here, and then this is the return edge, and then we have labeled it with ID 5. So that represents that this function call was made from this location 5. Okay. Now, uh, we can merge both of these together and try and decide not to give any label. So 4 comma 5, 4 comma 5 is equivalent to not even giving a label. So consider that there is no label. Okay, you call the function id from location from with value 4 here, and you go to the function id and then you return, and then you call this function id with value 5 from this location and then you return. So can you tell me uh, what can go wrong if we have a context insensitive graph? So what will happen if we have this context insensitive graph? So here we had labeled, let's say, all of the edges, like the forward and the backward edges, first with for value 4, and then here we had labeled them with value 5. And here we have not labeled these edges, let's say, with anything. So they are unlabeled. So then can you think of anything? Like, is there anything wrong with such a graph? So what may happen here is that uh, is it so it's is it possible like if I call this function id from here with value 4, and then when I have to return, then I return using this second edge, and I return here, and in this way I'll be able to skip this function call. Yeah. So here, when we were creating this call graph, sorry, the super graph, then we had, like say here, created this duplicates of this. So to enforce context sensitivity here, we had duplicated the CFG of red for first call and then for second call. So when we were calling from first location, we are calling here and then we are going back. And then if we are calling from second location, we are calling from here, we are going back. But consider that in context sensitive insensitivity, what is happening is that we don't have these two different copies. We have only one copy, and you are entering. You have these forward edges, two forward edges, and then you have the two backward edges. Okay, so that's what is being happening. That's what happening here. You can think of it like that, that in context sensitivity, if you have these two different copies, and so when you call from this location, then the first copy you're transferring control to the first copy and then you return back, and then you're calling from here, then you transfer control to the second copy and then you return back. But in case of context insensitivity, you have only one copy and you're going to transfer control from this location or this location. It goes to the same copy, and then that copy can return control to either of these locations. Both are valid locations here. Okay, both are valid return locations. So from this id function, now you can return either here or you can return either here. There is no label. Okay, like they have the same label basically, so you're not distinguishing between these two edges, so you do not know whether to return on this edge or whether to return on this edge. So that means that if you come to the function id using the above forward edge and you go back using the lower backward edge, then you will be able to skip the execution of this second id. So I hope that's clear. That's context. So that's what we, so far what we looked at is that control flow graph, how it is created. First of all, we are going to create per procedure. Then we are going to create the call graph. Then using the call graph, then when we have this call graph, in that call graph, basically, we are going to replace all of these nodes with these CFGs, per procedure CFGs, and that will give us a context insensitive supergraph. If we need a context sensitive supergraph, then we will have to look at every call location and then say duplicate or do something else. Now let's look at the CFI approach. Okay, so the CFI, so but before that, is there any question regarding the background? Okay, so if there is no question, let's look at CFI. So let's look at CFI. So in CFI, we are going to maintain this invariant. And what's the invariant? The invariant is that the execution must follow a path in the control flow graph created ahead of time. So you're going to create this control flow graph as I just described, and you're going to enforce at runtime when your program is executing that the program follows this control flow graph which was specified, which was created ahead of time. Okay, so now you will understand that if we create this graph in this context sensitive manner, then we will be able to enforce such then we will be enforce this. But if we create a graph, this context insensitive graph, then we will be enforcing this and still leaving the attacker the possibility to return to the second location instead of the first. So basically, if you create a precise control flow graph of the program and then see and you give it and then you use it with CFI, then the CFI provides the guarantee that at the execution, the program will follow the path in that CFG. Okay, but if you provide it uh, like a non-complete control flow graph or something, or a graph which does not have valid like which is not valid or which is a garbage control flow graph, then it will also not be able to prevent the attacks. So it all depends on the control flow graph that you are creating. Okay, and then there are these different methods to say, then what are the methods? First, the method is to create the control flow graph is that we can create it statically, like that at the compile time, we can look at the binary and then we can analyze it and then we can try to like create the CFG per procedure and then look at the function calls and then stitch them together and we can create it. Okay. Uh, but we will probably, I think, look at it. It's not always possible, as we have just seen here, like for some of the locations, especially like these return addresses or function pointers, we may not always know like what is the transfer location, where are we going to return, right? At the compile time we would not know, like that the compile time here, at least in on return we would know, because we will return only to the function from where it was called. uh, and But for the function pointers we may not know. But for that we can do a pointer analysis uh, over the program binary, and we can try to find out with pointer analysis that what we can create the superset of the functions id, the function pointers, which may be called from that location. Okay, so if there is a function pointer, then we can over approximate and we can find like which functions can be called with this function pointer. Now, what are we going to do is, once we have this CFG created, okay, and let's say we have created the CFG, then we are going to take the binary that we have in which we want to enforce this CFG, in which we want to enforce the CFI mechanism, and we are going to take that binary and then we are going to instrument that binary. Now, what does instrumentation means? So the instrumentation word means that we are going to add some new instructions into the binary. Okay, we are going to rewrite it. So we are going to rewrite the binary, and we are going to basically add some instructions to do some checks, ID checks. Okay, what are those ID checks? That will may become a bit more clear in the next few slides. Then once we have added these instrumentation into the binary, since this instrumentation will be, say, is being added by, say, a compiler, because I just said it's a compiler based mechanism. Okay, the compiler is adding this, but compiler is also a piece of software, and it's not a very small software. Okay, so it's a very large, it's software with a million, like very large code base and everything, and it's a complex piece of software, so it's not very uh, advice to put your trust into this compiler tool chain. Okay, so that's why we, to avoid putting your trust into the compiler, what we are going to do is that we are going to create a verifier, a binary verifier. Now this verifier is going to take the binary which is generated by your compiler, and then it is going to verify that the binary has the necessary instrumentations at the necessary locations to enforce the CFI mechanism. Okay, so what it is going to check is the direct jump targets. It's going to check the presence of the IDs, and the IDs are present, and then the check for IDs are present, and the IDs are unique. What are these IDs? We'll look with an example. And then when your program is run by the hardware, at that time, at runtime, these ID checks, which we have added in the binary through instrumentations, they will get executed. And if you jump to a location and where the ID does not matches, then that will cause your program to, like say, abort, because the ID did not match. So you can abort that process. So here you trust only the verifier basically. Okay. So you're not trusting the rewriter, binary rewriter. You're not trusting here the CFG creator or anything. You're just trusting this verifier to put the to check that the IDs check the IDs are unique and the ID checks have been put at all the necessary locations. And uh, so this binary has been instrumented actually with respect to the graph that was given. So you have to give a graph, and then the binary will be instrumented based on that graph, looking at that graph, that what what is this graph? Where are these control flow transfer uh, edges? So your graph will have the edges in your graph are basically control flow transfers. So your graph is providing the control flow transfer information. So if you give it a graph which is not complete and which is, then CFI will not work basically. So how are we going to build the CFG? Let's look at it. Now, again, I think it will probably become more clear with this. So this dot 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 is representing a direct call. This is a indirect call. Okay. So what are the direct calls? The direct calls in your program are those where your address is specified in your binary only. So at the compile time itself, the program at the compile time itself, the compiler knows that where you are. So like the address of the function being called. Like if you make a call to foo, and then the compiler, as we were looking at the GDB, when we are looking in GDB, we say disassemble, and then if you remember, if you recall, then the call instruction is like call and then some address, right? So that is a direct call, because there you have put the call in, after the call instruction, you have put directly the address where the jump should happen, where you have to go next. So those are direct calls. And now what is an indirect call? An indirect call is one where you do not know, like what at compile time, what is the target of this call. Okay. So example of indirect calls are return instruction. So at the compile time, you do not know what is the target of return, right? Only at runtime, this information is stored on the stack and it is read from the stack, uh, like what is the target of the return instruction. Similarly, the function pointers, those values are not known at compile time and they'll be known only at runtime. So these indirect call uh, jump targets are actually stored in the register. So uh, you do a like a jump to a register value. Okay. And so now here on the left hand side, you have this example, let's say, where we have one function sort2, which is taking these two in array, int A and int B, and then the length of the arrays. And it is going to sort these two arrays. Now to do the sorting, it is using here the sort library function, and it is passing, say, the array 1 here, array A here, the length, and then the less than. So it is sorting this array A in, say, the ascending order, and then it is sorting array B in the descending order. Okay. So here, if you note that to the sort function here, we are actually passing a function pointer. We are passing it LT or GT. So your sort function takes as argument as a function pointer. So in the first case, we are passing to it the pointer to the function LT, and in the second case, we are passing it the address of the function GT. Okay. And now if we look at this sort function, then so these are like the basic blocks in this function, sort function. So first is basic block is here, and it's terminating with the call to sort function. So the call to sort function it's actually a direct call, because we know that we are calling the sort function. So it's a direct call, and then you will transfer control to the sort function. Similarly, the second call to sort is also direct call, and you will transfer control to sort here. But if you look at the sort function, then it will look something like this, that there will be a call to some register value. So now this register will store the address of either the function LT or GT. So depending on the register value, the control flow can either go to LT or it can go to GT. Okay. So then uh, this is about the call forward edges. Now when looking at the backward edges here, that is the return edges. So when you're looking at the sort function, you can return to either first sort call, or you can return to either the second call here. Okay. So you can write return either to the first call, basically here, or you can return to the second call here. Similarly, in case of LT, actually you do not have two different like return, you do not have any two different return at destinations. Here the destination is only one, which is you will return after this call in sort function. Similarly for GT, you will return to this. Now what we have done here, what are these values, what are these labels here? So what we have done is that if we have, so we have here labeled all of these, we have categorized them. So if this return is can happen to these two different places, then we have given them the same label as here. And here, this location has the label 23, and and these two locations can return here. So we have like made a group of such locations which share either the jump target or the jump source. Okay, so we have here, yeah, so we have now here grouped these edges, and we have given them the same label. But by doing so, can you tell me whether this graph that we have created, is it a context insensitive or a context sensitive graph? Instrumentation rewrite should not ideally change the logic of the program, right? Yes. So the instrumentation is not going to change any original instructions in the program. It's only going to add some additional instructions into the program, which are going to like check, which are basically just check, which are checking the integrity of these control data in your program, like the return addresses, or something like that. Like not exactly return addresses here in this case, like what we are going to look at now, but it's not going to manipulate any instructions which are originally part of your program. It's just going to add additional instructions. Yes, so that's right. So this graph is context insensitive, because here you can return, so why is it context insensitive? Because you can call the sort function from this location, and then once you have executed the sort function, then you can use this second edge to return here. Okay, because both of them have the same label. So in this case, actually, let me also uh, tell you about why we have these label and what are they. So think of these labels. So it's like we have just labeled all of these locations. Okay, so this is, think of it like an ID, okay, which we were talking about earlier. So and when you are going to return from this when you're going to return from the sort function, then you are going to check whether the location that I am returning back to has the label 55. Okay, we're going to check for the label 55. So if you return here, it is okay. If you return here, that is also okay. So similarly here, when you return from here, you're going to check that whether the location that I am returning to has the label 23. So it has a label 23, so you can return here. But you cannot return, like for example, anywhere else. Basically, you cannot return anywhere else because any other location will not have this label 23. However, this is context insensitive graph, because here it gives you two possibilities to return from this return 55, because both of these locations have the same label here. So this is context insensitive. Okay. So so that's how we built the CFG. And now let's look at how do we instrument the binary. Okay, so like this here is call 17 comma r. It is going to transfer the control to to the address which is stored in r register only when the r has label 17. Okay, so we are going to instrument the binary to add this check that okay, transfer this call, transfer the control to the location stored in R only if that location pointed to by R has the label 17. So that is like that's the check we are going to do. So for that, what we have to do is that we have to insert this number, unique number at each destination. So if you will see that this 17 label is currently unique in our it is unique in our example. So this 17 label is only present in the LT beginning of this LT function and the beginning of this GT function. Okay, so it's a unique label with respect to this call because this call can trans can because from this call instruction we can both of these are valid destinations, and both of these valid destinations have the same label 17. And then we are going to insert a unique number at all the valid locations from this call instructions, from this particular call instruction. And here there are only two valid locations. So we are putting this label 17, two locations. And two destinations are equivalent if the CFG contains edges to each from the same source. So the two destinations are equivalent if the CFG contain edges to each from the same source. So here the source is same, right? And it contains edges to these two different places. So that's why we have combined these two destinations as, and we treat them as equivalent and give them the same label. Similarly, I think destinations. So that is for destination. Yeah. Similarly, here we are returning from here, and this place has the label 23, and we can return from other place like here also. That, but we are returning to we can only return at this location whether we are in LT or we are in GT. So we have given the label 23 here, and then in the LT function we have this ret instruction which is going to check that it is going to transfer control to the address, to the return address, only if that return address has the label 23. Okay, so for the calls and the return instructions in your program, we add additional instructions. Okay, and these additional instructions are going to enforce this behavior that if the call is made to address stored in R, and we are particularly talking about here only indirect calls because only in those calls addresses can be modified by the attacker. The attacker cannot change the direct calls. So the in case of an indirect call, the we are going to check that the control is transferred to the address stored in R only if that address has the label which is specified with the call instruction here. Similarly, in case of return, we are going to check before we return that the address where we are returning has the label which is specified with this return instruction. Okay. Is that clear? These labels are, it has context. So this is okay. It has context insensitivity. And these labels are assigned by the verifier. No, these labels are not assigned by the verifier. These labels are assigned by the instrument writer. Sorry, instrument, the binary rewriter. which can be a compiler or it can be just another binary writing tool. Okay, so we can either do it in the compiler, or we can do it like at the source code, using the source code, or we can do a binary rewriting. And these IDs are going to be assigned by the binary rewriter. Okay? The binary rewriter is going to choose these IDs. It needs to maintain that these IDs are unique. It needs to put these, add these IDs and put these ID checks. It needs to add, of course, these IDs into your program, like this label. It will have to add these IDs, like label these locations. So that it means ID, add ID. It needs to put the ID checks at, say, call instruction, return instructions, and it should maintain the ID uniqueness. What your verifier is going to do is it is going to take the binary which has been rewritten by the instrumenter. It is going to take that, and then it is going to check that it has instrumented all the jump targets which are not direct jumps. Okay, the it has the added the IDs and ID checks, and also going to ensure that all the IDs are unique. So that your verifier is going to do. Now, why have this verifier also? That is because we don't want to trust the binary rewriter. So the binary rewriter, say, can be a compiler, and since the compiler can be a huge code base, and we do not want to trust the compiler, we want to reduce our trusted computing base. We want to trust the trusted computing. We want to reduce the trusted computing base. That's why we can just write a simple verifier ourselves, like, which will not be as complex as a binary rewriter. We can write it. It's a simple verifier, and since here, but basically the argument is that since the verifier is a simple piece of code with less number of line of code, it is less likely to have bugs, and so we have reduced our trusted computing base. And that's why we do not trust the complex rewriter, and we trust only the simple verifier. Okay, I hope that clarifies the doubt. And now, but the question here is that, so I'm saying that, okay, at the call instruction, we are going to check that transfer is sent to this location only if the location has this label R. But your call instructions in your x86, not x86, I mean your call instruction, at least earlier, now the hardware actually has support for CFI. But earlier, when this work was, say, proposed, at that time the hardware did not have support for CFI. So the instruction set did not have any instructions which would allow you to do this thing, that which would allow you to which would allow you to call a function uh, like on a conditional, like on a condition, like it was not, a single instruction was not present. Basically, that's what I'm trying to say. A single such instruction was not present. So how did the authors of this paper implemented it? So the authors of this paper, so this is an instrumentation example from this work, CFI work. And how did they do it? So let's see that this is the original code, okay? And this is the instruction, which is jump ECX. Okay, and let's say that this is the jump in ECX is your uh, like it's similar to the call instruction, right? It's just a jump. It's an indirect jump. You're going to jump to the address pointed to by ECX. And let's say that the destination is this instruction, move EAX, comma ESP plus 4. Let's say that this is a valid destination for this jump instruction, which we have found with the help of our CFG. Okay, so now what we are going to do is we are going to add instructions, which we are calling instrumentation. So this is see that this is your jump ECX, and before we have added these instructions, and these instructions are instrumented instruction. These are instrumentation. Similarly, on this side, this is your original instruction, which is move EAX comma ESP plus 4, and this is your instrumentation. Here, now what are we doing here now? Let's look at this. I hope it is visible. And then look at this like instruction by instruction. So the first instruction is move EAX, comma 1, 2, 3, 4, 5, 6, 7, 7. And so it's moving the content. It is moving this value 1, 2, 3, 4, 5, 6, 7, 7 H into EAX. Okay, then you are incrementing the value of EAX. So now EAX contains the value 1, 2, 3, 4, 5, 6, 7, 8. Okay, then you have this compare instruction here. Compare the value at location pointed by ECX, because you're trying to jump to ECX, right? So it's saying compare the value pointed by the address stored in ECX plus 4 with the content of EAX. So compare it with value 1, 2, 3, 4, 5, 6, 7, 8. So this 1, 2, 3, 4, 5, 6, 7, 8, which is now computed in EAX, is actually your ID. Okay, and if the ID does not match the value, then you are going to jump to this error label. Otherwise, if the ID match, then you can jump to the ECA, to the location. So jump to the destination only if the tag is equal to 1, 2, 3, 4, 5, 6, 7, 8. Now, how have we now stored this tag on this side? So to store this ID on this side, they're saying that they are using a x86 assembly instruction to insert 1, 2, 3, 4, 5, 6, 7, 8 tag into the binary. So for that, they're using this prefetch NTA instruction, which does nothing, but it's like a prefetch instruction, which is going to prefetch this value into the cache. Okay, so it's going to prefetch this value into the cache, and it does nothing. So that's why they're using this assembly instruction. And so they have just used this, and they were able to add the ID here. So that's why if you will look at here, that it is actually, it has like started adding these, 1 second, ECX. So that's why if you will see that ECX value here actually would have been changed. So ECX will now point here, okay? And then the ECX plus 4, if I'm not wrong, I think, then the ECX plus 4 is your ID here. And that's why it's comparing this ECX plus 4 with EAX. So your EAX here has the value 1, 2, 3, 4, 5, 6, 7, 8 computed by the first two instruction, and then it is comparing it with the ECX plus 4, which is this value, which is part of your program code, and then it is going to jump to the ECX address only if the comparison succeeds. Okay, so the call instructions like this are modified in this way. Okay, now you may wonder that why did it not move EAX, 1, 2, 3, 4, 5, 6, 7, 8 directly into EAX and then just compare that? So can you think of like why did we do it in two steps? Like first move EAX, 1, 2, 3, 4, 5, 6, 7, 7. Then we incremented the value of EAX and then we compare. Why not just move this ID into EAX and then compare? So the reason for this is that if you will write here directly the ID 1, 2, 3, 4, 5, 6, 7, 8, then that can also be treated as a valid jump destination. Because a destination is valid if that has this label. Okay, if any location which will have this ID present will be treated as a valid jump location from this place. Okay, so that's why it will be then able to jump here as well, and we do not want that. So to avoid that, uh, they have first moved the ID -1 value into AX, and then they increment it. Okay, is there any question? Okay, so if there is no question, and then let's continue. So here in C, to the verifier that we have for CFI instrumentation, it's going to verify these three things. Okay, first it's going to verify the direct jump targets, which means that it is going to look at the targets of the direct jump instructions, and it is going to check whether these direct jump targets are valid according to the CFG or not. Second, it is going to check that every entry point has a valid ID. Okay, every entry point has a valid ID. It's going to check, does the ID appear in the binary by accident? So it's going to check that the ID is present only at the valid locations and nowhere else in the binary, and not even accidentally. Uh, so how can it be accidentally present in the binary? So it can be accidentally present in the binary if this byte sequence can be created within the instruction stream, like the machine code. So the machine code is also like this, right? It's just a byte sequence. So the ID can be present inside the binary by like it can be just present somewhere in the binary uh, a priori. So so that's why it needs to check that the ID is unique, in the sense that this ID should not be present anywhere at all. Like it will have to check all the entire binary, and it is going to have to check, say this is say 8 bytes, then it will have to check every 8 bytes, even like not like 8 bytes, even like shifted by 1 bytes. So it have to check every location, and then it will have to check that the binary doesn't contain a ID accidentally. Second, it is going to check that the ID checks are placed on all the control transfer instructions, and that the checks respect the CFG, that they are according to the CFG. And we are going to trust this verifier. So the assumption here is that the IDs are unique, okay? And this is required to preserve the CFG semantic, and then the code is non-writable, and then the data is non-executable. So revisiting the assumptions here, so why do we need unique IDs? So we need unique IDs because we can so that we can only jump to a valid target. So say if you can from sort, you can call only these two location. Sorry, sort is a direct call. Yeah, from here you can call only these two locations. Then the ID should be present, right? And it should be unique. That ID 17 should not be present anywhere else. Otherwise it's allowed to jump there. Then the non-writable code. The code should be non-writable. And I think now it has become more clear that why we had to put this assumption. We had to put this assumption because if the attacker can change the code, then the attacker can remove these checks or can change the ID or basically can do anything. So that's why it's important that the code is non-writable. Then the non data must be non-executable data. Why is it required that the data is non-executable, because then the attacker can put any data or can put anything on your like it can write its own code in the says the stack, and then it can add a label before that, that is expected, and then it can cause the execution of that uh, labeled data that it has written. So that's why it's important to have a non-executable data and non-writable code. So both of them are required. These are the assumptions, and the security guarantees that are provided by CFI is: the first is that it is effective against the attacks based on illegitimate control flow transfer, like stack buffer overflows, return to libc exploit, and pointer corruption, etc. So with CFI in place, you will not be able to corrupt the control flow transfer, like basically cannot transfer to a invalid location, a location which is not valid with respect to the CFG as determined by the CFG. However, it does not protect against the attacks that do not violate the program's original control flow graph. So as we had looked, there are these the data only attack or the non-control data attacks, which only modify the data and not the control flow of the program. So they are not prevented with CFI. And let's say you're calling a system call or another function and you're passing the arguments. And if you change the arguments, then that is also not prevented with CFI. Any incorrections in the logic cannot be prevented. If you change the file names, that cannot be changed. So basically, any sort of an attack which does not modify, which does not tries to modify the control flow of the program, uh, like to an invalid control flow transfer, then those will not be detected with CFI. And so with this, we have discussed what CFI is, and now I will stop and you can tell me if it's clear or not. So the CFG here is actually used as an input to the binary rewriter. Okay. And that's all. That's when the purpose of CFG is finished. And the attacker don't even need to modify the CFG. So we are assuming that the so I think maybe what you meant was that before the CFG is given to the compile binary rewriter, if it's modified, yeah, that's a possibility. I mean, of course, there are so many attacks. Uh, but let's assume that that's not happening. But yes, if the CFG is modified, if the CFG is not contains the valid uh, control flow transfers, and if the binary rewriter is going to generate a binary according to that, then that again will be verified by the verifier. So then the CFG which is being used by the verifier, if that is also corrupted, then of course then that's a problem. But then we can assume here that the CFG which is used by the verifier and the code of the verifier, those two are trusted to be safe and beyond the attacker's reach, that the attacker is not able to modify these two operations. So if that is that is true, then this with CFI, we will be able to generate a correctly instrumented program binary according to the CFG which was provided. So I hope that's clear. So it's whenever we have this any like the question that you asked is very valid, and it's uh, just defines that the attacker model or our assumption that the what assumptions we are making here. And it's very important to specify these assumptions clearly, and to know that and to also know that the mechanism is secure as long as only those assumptions hold. If the assumptions do not hold, then the mechanism is no longer actually secure. I hope that answered the question. So if anybody has any other question, okay, thanks. So I hope so that's all actually I had for CFI. In the end, we have this evaluation from this paper, but this paper is very like since it's from 2005, these numbers are old, and of course now newer. There has been new implementations of CFI. Now regarding the implementation of CFI, so what like the LLVM compiler tool chain actually has an implementation of control flow integrity. So if you want to say look at that, then you can compile your program with LLVM tool chain, and then you can inspect the binary which is generated. And you can also go and check how the LLVM compiler is actually like implementing this control flow integrity. And the control flow integrity, like what they will be implementing is definitely going to be more complex than what is being done here. Uh, and so uh, that's all. Like it's a compiler based defense which is implemented. Like you can set you can enable that in LLVM, and if you will enable that flag, then your program will be compiled with these checks. Okay, and then as per my knowledge, I think for now these CFI techniques they have been optimized. They've been optimized quite a lot. Here you can say that the overhead enforced is around 40%, but that's no longer true. The CFI techniques, like nowadays, they have less than 10% overhead, and that's another thing. Another thing is that the CFI, for the CFI, we said that the hardware does not support any instructions to do something like this. And that is also the Intel hardware had added support for uh, CFI. So it had, I think, the Intel CET, Control Enforcement Technology. So CET, if you're interested, you can go and read about that. So it has added the special instructions and for implementing the control flow integrity checks and all. I think that's it. So that's it about the control flow integrity. And now if probably we can go back to the table we were creating. Yeah, here, and let's see for the control flow integrity. So that with control flow integrity, can you prevent data corruption? And keep in mind that control for control flow integrity, your W XOR X is a assumption. So you have to assume that it is present. So no, right? We just discussed, no, in the slides that it cannot prevent the data corruption attack. It can only prevent it is only adding these checks at these branch transfer instructions. Okay, it's only adding the check at the branch transfer instructions, which are checking that the destination where you're transferring the control to has the same label that you have specified as say in this call instruction. So it's checking for these labels or these IDs only at these transfer instructions, and apart from that it is not doing anything. It's not checking any the integrity of any other data. So that's why it does not prevent the data corruption. Then execute code on the stack, is it prevented? Execute code on the stack. Yes. So it is going to prevent the execute code on the stack because of the WXOR assumption. Now for return to libc and return oriented programming, can you quickly again tell me that whether it is going to be able to prevent these two attacks, and why will it prevent? If so, then why can it prevent these two kinds of attack? Mm, yes. So all of these are correct answers only. Actually, yeah, not because they're not part of the control flow graph, but actually because they will be not having the correct ID checks. When we are doing this control flow integrity, then these library, we can also add the control flow integrity to the library function calls as well. Okay. Uh, so But here we are going to be able to prevent the return to libc and return oriented programming attack, because now when we are trying to return to a invalid to a library function, then the ID check will not match. Okay, so the ID check will not match. So that's why it's going to prevent it. Now, format string non-control data corruption. So similar to the first one, it cannot prevent it because it cannot do anything when it comes to non-control data. And the last one is control data corruption with the format string vulnerability. So can it prevent that? Yeah, so the format string vulnerability will be able to corrupt the data, and but the control flow integrity defense will be able to detect the corruption, and therefore it will be able to prevent the attack from happening because again the ID checks will not be present. So I hope that at least on a high level you would understand why control flow integrity is working. Of course, what I have presented today is the first it's like the most simplest control flow integrity. We did not even go into the other details about it. Uh, so if you're interested, you can uh, read the paper, you can you can Google for control flow integrity, and I think the first paper. Anyways, I think I lost my slides again. Anyways, you can search for the control flow integrity. Yeah. So you can look at this. So this is actually the first paper, which this is the first paper on control flow integrity in 2005, which we just looked at now. And then you can find more papers on control flow integrity if you're interested. Now, since we are already uh, like close to 7, so I will skip on memory bound checkings, which I had planned to cover. So tomorrow we will start with memory bound checking, and I will not go into too much details about this tomorrow, but we will just understand the basic idea about bound checking, and then we are going to fill this table, and that will basically complete our entire this exploit versus defenses table. After that, tomorrow, what I plan to do is that I plan to then talk about trusted execution environment and and then we are going to look at uh, one particular trusted hardware, which is the ARM trust zone. And then we will also look at how we can, like say, use the ARM trust zone. So I will, so there is a open implementation for like which enable us to access the trust zone, which is called Opti. So then we are going to uh, have look at that, like how you can say install Opti, and then how you can uh, work with that. So we will look at that example so that you can learn to use say ARM trust zone. After that, we will look at, I think, virtualization and containers, and then we will see. So that will be the plan for tomorrow. With that, we would have covered these different attacks, defenses, and then we would have looked at the trusted computing. And I think if time permits, then I can also present my like my recent work, which is on attestation, and which is like control flow attestation. So what we have, yeah, so I can also look at control flow attestation. It's like similar to control flow integrity, that I can also discuss. But before I end for today, maybe I should add here that. Uh, don't move my slide. So before I end for today, maybe I should add here that uh, for the for so in this table, even with control flow integrity or some or with other defenses, we are not able to prevent these data only attacks, right? So for those kind of attacks, we have different class of defenses, which are called return oriented, like which are like data flow integrity defenses, which prevent the integrity of the data which is stored in your program. And so those will be the defenses for the class of attacks which only target the data in your program without changing the control flow of the program. So I think that is all from my side for today. And if you have any questions, then please feel free to ask them. And otherwise, we will end for today and we'll meet tomorrow. Is there any questions? Okay. Yeah, that's all from my side. So if there is no question, then we can end our discussion here for today, and then we will meet tomorrow. Thank you very much, everyone, for joining, and let's meet tomorrow at 10 a.m. Yeah, thank you, everyone. I will put the recordings on YouTube, and I will share the links on the chat box here, because I think the chat box is available to is accessible to everybody. So I will put the link to the YouTube videos here in the chat box uh, for today's recording. Thanks, everyone. I'll stop the recording.